Hi, in this video we're going to introduce the ideas of orthogonal and orthonormal bases and the Gram-Schmidt process that allows us to find them. Let's begin with a few definitions. What do we mean by an orthogonal and an orthonormal basis? These ideas are really quite simple. An orthogonal basis is simply a basis, that is, a linearly independent spanning set for a vector space, where all of the elements of that basis are orthogonal to one another. That is, the dot product of Vi and Vj is equal to 0 for all pairs. An orthonormal basis is a special kind of orthogonal basis. So again, it's a basis for a vector space where all of the vectors are orthogonal to one another, but we also add an additional requirement that they have a length or norm of 1. Recall that the norm of a vector is simply the square root of its dot product with itself, and thus for the norm to be 1, the dot product has to be 1. So we can write this requirements that the dot product of every Vi and Vj is equal to 0 for all I not equal to j, and the dot product of Vi with itself has to be 1 for all of the I. We make these definitions because things become very much simpler when we are working with orthonormal bases in particular, but even when we're just working with orthogonal bases. Let's take a look at one of the ways that things become simpler. We've discussed in the last section, or in the last video, the idea of projections and pseudo-inverses that we can use to solve for a least squares solution, a best approximate solution in the case where we have an inconsistent system. And the projection was given by this general result. The pseudo-inverse was given by this general result. And both of these include this A transpose times A all inverse term. These are kind of messy things to calculate, expensive things to calculate, because we need to first of all take a matrix product, and then we have to invert that matrix, and then we have to take another matrix product, and so on. Let's think a little bit about what this ATA looks like. Well, the columns of A in this form are simply the basis vectors, the vectors of a basis for the vector space we're dealing with, which means if we take A transpose times A, we are going to end up with the result shown here. A transpose will be V1 transpose, V2 transpose, and so on, to Vn transpose. And if we multiply that by A, we're multiplying this by V1, V2 to Vn. What do we do in each step? We walk along a row and down a column, giving us the dot product of V1t and V1 for the first entry, and then along the same row and down the second column to give us the entry for the second column, and so on. Okay. This is general. This is what this A transpose A always looks like. However, in the case where we have an orthogonal basis, let's just worry about the orthogonal case for now, all of these off-diagonal elements, all of these V transpose 1V2, dot product V1 Vn, V2 Vn, anything that isn't on the diagonal is 0. The transpose, so this A transpose A becomes a diagonal matrix, and matrix inverses are easy for diagonal matrices. So to summarize, we have our columns of A. If they are an orthogonal basis, we have this constraint that the dot products are 0 for all of the non-equal ij, giving us this diagonal ATA. Why are these easy to diagonalize? Because for a diagonal matrix, the inverse is simply given by another diagonal matrix where we take the inverse of every element. So the inverse is found simply by writing the same diagonal matrix, and taking the reciprocal of each of these terms. A very easy thing to do. Not only is this an easy thing to do, this also leads to some very important results. So let's continue looking at this projection with an orthogonal basis and see where it takes us. The next step after taking the inverse of A transpose A would be to multiply this by A transpose U. Let's think about what this product looks like. This product looks like this diagonal matrix multiplied by A transpose, which is a matrix that has all of the vectors of our basis as rows, multiplied by U, which is a column matrix. This small product here, this sort of first pair, this A transpose T, what would this give us? We would walk along a row and down a column, along a row and down a column. This would give us a matrix that simply takes the dot product of each row of V with U. So every row of this will be a column vector where each entry is a dot product. When we then multiply by a diagonal matrix has the effect of scaling each row by the diagonal entry, and we end up with the form here where the numerator in each of these terms is this Vi transpose U that comes from this product A transpose U, and the denominator is the scaling factor from this matrix here. You already might start noticing that the entries in this vector look remarkably like the part of the projection of a vector onto a vector, and we'll see that this relationship becomes even deeper in a moment. So now let's put this whole thing together. Now let's find the entire projection. We just have calculated this A transpose A all inverse times A transpose U. Now we want to multiply by this additional A. We have a vector whose columns are V, a matrix whose columns are V, and a column vector whose entries are these ratios of dot products shown here. Well, we know that in the column view of the column picture of a linear system, I could really think of this is just some A times X, where this whole piece here is X. In the column picture of a linear system, we can think of this A times X as being some X1 times the first column of A plus X2 times the second column of A, and so on. And so let's see what that gives us if we interpret it this way. Our coefficients in this expansion are these individual terms from our vector. And the columns of A are these V's. And so each term has a scalar and a vector. And we are writing this combination of scalar multiples of the vectors, a linear combination of the columns of A, where the coefficients are given here. Now, let's take a look at what each of these terms looks like. N transpose times U, the dot product of Vn with U, divided by Vn transpose Vn, the dot product of Vn with itself, multiplied by Vn. This is exactly the result that we found before for the projection of a vector onto a vector. When we have an orthogonal basis, the projection onto the vector space is simply the sum of the projections onto each individual basis vector. We don't need to do this big complicated matrix product. We can simply write the projection as a sum of individual vector onto vector projections. Very important to note, this only works when we have an orthogonal basis. This result depended on us having a diagonal A transpose A. All right. So we see that when we have an orthogonal basis, things become easier. A transpose A, the inverse is diagonal, so the inverse is easy. We end up with this result that we can simply sum up individual projections onto vectors to get a projection onto a vector space, and so on. Things become even easier if we have an orthonormal basis. For an orthonormal basis, we still have the same constraint that the dot product of the non-equal basis vectors are 0. So that means A transpose A has to be a diagonal matrix. But we also have the result that each of those lengths, the lengths of each of those basis vectors is 1. And so that means this diagonal in AA transpose is all 1s. A transpose A is just the identity matrix. We're interested in A transpose A inverse, but of course the inverse of the identity matrix is also the identity matrix. And so what this result means is that when we have an orthonormal basis, this A transpose A term simply disappears. We essentially remove it from the projection. We remove it from the pseudo-inverse. We end up with a result that the projection is simply A transpose U, a double matrix product, and the pseudo-inverse is just the transpose. Remember that the pseudo-inverse is what we use to solve for least squares solutions when we have an inconsistent system. If we only had to multiply the right-hand side by the transpose, that would make things incredibly easy for finding least squares solutions. Okay. So we've seen that orthogonal bases, orthonormal bases, are very useful for simplifying problems, especially problems involving projections and least squares and so on. How do we find one? Or are we just limited to the cases where we, by luck, are given an orthonormal basis? The Gram-Schmidt algorithm is a robust process to generate an orthonormal basis starting from any basis. One of the themes of linear algebra, one of the recurring things that we see is that part of linear algebra in any way is the development of robust algorithms that let us solve problems. Gaussian elimination is a robust algorithm to solve for the set of solutions to any system. Right? LU decomposition is a matrix representation of that algorithm. How do we develop a robust algorithm to generate an orthonormal basis, which will then be able to easily solve least squares solutions, approximate solutions? The ideas we are going to use in the Gram-Schmidt algorithm, and there's a few key foundational concepts, all that we've seen before. One is that the projection can be used to express a vector as a sum of parallel and orthogonal components relative to some vector space. Recall that if we have some, we'll take the example of a line. If we have a line of a vector space and some vector v, right, we can always break this down into a orthogonal component u, orthogonal, and parallel component u, parallel. We can do this when the vector space is a line, when it's a plane, or anything. And we know that this parallel component is given by the projection, and the orthogonal component is given by the difference of the original vector and the projection. So the projection lets us split vectors into a parallel and orthogonal component, and projections are easy when we are working with an orthogonal basis set because they're just the sums of the projections onto the individual basis vectors. And then that makes it a lot easier to evaluate projections rather than having to take all of these matrix inverses repeatedly and so on. Finally, when we can always create a unit vector in the same direction of any vector simply by dividing that vector by its length. The first two pieces of these are going to be used to generate an orthogonal set, and the last piece is going to turn that orthogonal set into an orthonormal set. So let's walk through now in more detail how we're going to do this. Our starting point, we're going to try to find an orthogonal set. Starting with any basis for a vector space, some set of vectors vi, where we will assume they are a basis, they are linearly independent. Let's create a new basis, we'll call these wi, that is an orthogonal one. Vi and wi will have, v and w, these sets will have the same number of vectors in them because they are both bases. They have to have the number of elements as the dimension of the vector space. So how do we do this? Well, we're going to take a step-by-step process, adding one new vector to the set of w at a time, building them up to be orthogonal. The first thing we do is we just take one vector from the original set. Generally, we phrase this as the first vector, but conceptually, there's no reason that we couldn't reorder these vectors in any way we wish. Right? So there's some arbitrariness in terms of which the first one is. We usually take the first one in the list. The first vector of the new basis is just the first vector of the original basis. That is, we simply make an assignment that w1 is equal to v1. This one vector spans a line. So if we now think about what is the set spanned by the new set is a line. Let's call this w1. We then want to construct a vector that is orthogonal to this line, right? But still in the original vector space. This line sits in the original vector space because it was made from a vector that is part of the original vector space. We now want to construct another vector that is orthogonal to this line and is also in the vector space. How do we do this? We take a second vector from the original set, v2, and we find the component of that vector that is orthogonal to this line. How do we do that? We take the vector minus the projection of the vector onto that line. So some v2 minus the projection of v2 onto w1, and that's what our w2 is going to be. Here, we take advantage of our understanding that the projection onto a vector space is just given by the projection onto the basis of that vector space. W1 is a basis for this line, so we subtract from v2 the projection of v2 onto w1, which is given by the ratio of the dot product of w1 and v2 divided by the dot product of w1 by itself multiplied by w1. This now gives us a second vector. These two vectors span a plane that is part of the original vector space, a plane that sits in the vector space we started with. We'll call this plane W2. The next step, presuming that we have a third vector, which we almost always will, is to once again find a vector that is orthogonal to this plane by drawing a third vector from the set, some v3, and finding the component of that is orthogonal to the plane we just defined. v3 minus the projection of v3 onto that plane of the two vectors we've already selected, and take advantage again of the fact that this W2, we have an orthogonal basis for it, and so we can represent the projection of v3 onto this simply as the projection onto v1, onto w1, and the projection onto w2. So we subtract from v3 the projection of v3 onto v1, given by this form, and the projection of v3 onto w2, given by this form. This now gives us three vectors that are by construct orthogonal to one another, and which span some three-dimensional subspace of the original vector space we started with. In the kinds of problems we work through by hand, this will often be the stopping point, because construct problems to give you a flavor for how these work without overly burdening the amount of work you need to do on paper. But the algorithm can continue for as long as necessary. If we have an n-dimensional vector space, we will continue for n steps. Every step, what we do is we add one more component by drawing a vector from the original set and subtracting from that the projection of that vector from the orthogonal set we have already defined, and that creates a new subspace of one dimension higher. At each of those stages, because we already have an orthogonal basis for the W's, we can compute that projection very easily, simply as a sum of projections for individual basis vectors. Our general rule then can be written something like this. We select a new vector from the original set, and then subtract off the projection of that vector from the first orthogonal vector, from the second onto the second orthogonal vector, onto the third, and so on, until we have subtracted off all of the components necessary. This gives us another orthogonal vector, and we continue. Once we've done this, once we've completed this process, we will have a set of vectors W, n of them, where their dot products are all 0, and which span the original set. That is, we will have an orthogonal basis. This is an orthogonal basis. It is not an orthonormal basis. How do we get an orthonormal basis? This part is easy. We simply take each of these vectors and we divide each one by its length. And if you just think about it, if we start with some vector that has an arbitrary length, let's say I have some x, and its length is the norm of x. What is a vector that, what does it look like if I define some x hat equals 1 over the norm of x times x? Well, it's a vector that's in the same direction as x, but it is 1 over the length times shorter. That is going to be a vector that is in exactly the same direction of x, but has a length. That has a length of 1. So this will have length 1. And this is the process we're using here. We're going to take each of these vectors, divide them through by their length, and that will give us then a set of vectors that spans the original vector space, that has dot products between all pairs of 0, and that has lengths. Sorry, this should be a Q here. It has lengths of each of these vectors equal to 1. An orthonormal basis. Okay, probably the best way to get a feeling for what Gram-Schmidt is, how it works, is to walk through an example. Let's start with a set of 3 vectors, a basis of 3 vectors in a 4-dimensional space. So these will span some 3-dimensional subspace of R4. They're not orthogonal. We can look at the dot product of the first one and the second one, and it clearly does not give us 0. They are not unit vectors. How can we construct an orthonormal basis for this same vector space? We use Gram-Schmidt. The first step is simply to draw out the first vector and to assign that to the first vector of our new basis, W1 equals V1. Okay. First vector is always trivial. The next step, we want to generate a second vector. What we do is we take the second vector in our list, and we need to work with this one. We start with that vector, V2, but we need to subtract off the projection of that vector onto the one we already defined. What's the dot product of W1 and V2? So what the dot product, W1, V2, we get by multiplying corresponding entries and adding them up. 1 plus 1 plus 1 times 2 plus 1 times 4 plus 1 times 2 plus 1 times 1 is 10. So that's where we get this 10 here. What is the length of W1? This is the sum of the squares of each of the elements of W1. 1 plus 1 plus 1 plus 1 plus 1 is 5, giving us here. So, obviously, 10 over 5 is 2, so we're subtracting 1, 2, 4, 2, 1. So we take 1, 2, 4, 2, 1, or V2, and subtract from that 2 times 1, 1, 1, 1, 1. 1 minus 2 is negative 1, 2 minus 2 is 0, 4 minus 2 is 2, and 2 minus 2 is 0, 1 minus 2 is negative 1. This is our second vector of our set. Now we have a plane that's in 4-dimensional space, but our original space was a 3-dimensional vector space. We need to continue on. We need to add another vector to our basis. We take the third vector from the set for this and work with use that as a starting point, subtract off the projection onto the 2 previous vectors we have already seen. At this point, it is very important to remember that we are taking the projection of one of the original set onto the new set. This is essential because it's only the new set that is orthogonal. Right? So in each of these expressions, only the V3 comes from the original set. All of the rest come from the new set. Okay. So V3 is 0, 3, 4, 3, 1. What is this? The projection of V3 onto V1, or sorry, onto W1. Well, we have W1 given here. We've already computed the length of W1. We did that for the previous case, and we saw that it was 5. We need the dot product of W1 and V3. W1 transpose V3. We multiply corresponding entries and add them up. 0 plus 1 is 0. 3 times 1. 4 times 1. Plus 3 times 1. Plus 0 times 1. 0 plus 3 plus 4 plus 3 again equals 10. So we get the same coefficient here, but by coincidence, not because it's actually computing the same thing. So we're going to subtract 2, 2, 2, 2, 2 from 0, 3, 4, 3, 0. Right? This piece would give us 0 minus 2 is negative 2, 3 minus 2 is 1, 4 minus 2 is 2, 3 minus 2 is 1, and 0 minus 2 is negative 1. But we still have to subtract off another piece. We have to subtract off the projection of, again, V3 onto W2. W2 is our vector here, negative 1, 0, 2, 0, negative 1. What is the length of W2? The length of W2, the denominator here, we get by taking the sum of the squares. 1 plus 0 plus 4 plus 0 plus 1 gives us 6. And then we need the dot product of W2 with V3. Dot product of W2 with V3. We add the product of corresponding entries. 0 times negative 1 is 0. Plus 3 times 0 is 0. Plus 4 times 2 is 8. Plus 3 times 0 is 0. Plus 0 times negative 1 is 0 is 8. 8 over 3, or 4/3. So to get our final result, negative 2 plus 4/3 is negative 2/3. 1 minus 0 is 1. 2 minus 8/3 gives us negative 2/3 again. 1 minus 0 again gives us 1. And negative 2 plus 2/3 again gives us, or sorry, plus 4/3 again gives us negative 2/3 for our final vector. At this point, we have a 3-dimensional vector space. orthogonal vectors, the span of this set is the same as the span of our original space. Right? This is an orthogonal basis. Has the same number of vectors of the original set, so the dimension of the span is the same. They were all derived as linear combinations of these, so they're in the same vector space, but they're all orthogonal. The last step is to convert this to an orthonormal basis. How do we do this? We divide each of these by their length. Right? We've already computed the dot product of each of the first two with themselves. We saw that the dot product of W1 with itself was 5, so its length is square root of 5. The normalization factor is 1 over square root of 5. For Q2, we've seen that the sum of the squares is 6, so the length is square root 6. The normalization factor is 1 over square root of 6. And for this one, we need to compute it. It will often be the case working with Gram-Schmidt that we end up with fractional answers, especially towards the end of the process. Computing the norm of these can be a little bit of messy arithmetic. A trick that can be used to simplify that is to first of all scale this vector to make everything integers, and then to normalize that. The idea behind this is that we can start with some vector. Oh, sorry about that. We can start with some vector of a certain length. What we want to find is a unit vector of the same length, a unit vector in the same direction. But what we can first of all do is we can find a bigger vector that is some scalar multiple of that original. And so maybe call this, let me call this U, and we'll call the original vector X. And if we were to we can get a unit vector, maybe do this in cyan, we can get a unit vector here, X hat. We can find this by taking the norm of X times X, but we can equally get this by taking the norm of U, 1 over the norm of U times U, because it is a unit vector, and any unit vector in the same direction is going to have the same basic structure. So it's going to be the same. So we can multiply this vector that has a bunch of fractions in it, multiply this whole thing by 3 to give us, this should be a 3 and a 3, sorry, to give us -2, 3, -2, 3, -2. And sorry, and this is then wrong here also. Made a mistake here because I had a typo there and I used those. The length of this vector is 4 plus 9 plus 4 plus 9 plus 4. 4 plus 4 plus 4 is 12. 9 plus 9 is 18. So the sum of these is 30. We divide this by 1 over 30 to give us our final answer. Okay. When we go through the process of Gram-Schmidt, we will almost always end up with vectors where we have scaling factors that are 1 over radicals, 1 over square roots. And it is not uncommon to come across fractions. This is just part of the nature of Gram-Schmidt. In order to have an orthogonal basis, and especially to have an orthonormal basis, we can't limit ourselves to simple integer numbers most of the time. Okay, this should give you a feeling for how Gram-Schmidt works. I want to wrap up with just mentioning one very important idea for computational linear algebra, although one that we use much less often working through problems by hand. And this is the idea of the QR decomposition. Remember that we saw for Gaussian elimination that we could represent the process of Gaussian elimination, right? This A, and actually more strictly A going to an A prime with row exchanges and then going to U, could give us a PA equals LU, right? Where we have A in here as our starting point, we have U in here as an ending point, and P represents the row exchanges, and L represented the steps of forward elimination, actually reversing them. It turns out that we can do something very similar with Gram-Schmidt, right? So let's think about how that works. First of all, let's just imagine that we arrange our basis vectors as the columns of a matrix. So instead of a set V1, V2 to Vn, we'll call that a matrix A. Then we can think about the process of creating, first of all, an orthogonal set W, and then an orthonormal set Q, as transforming this matrix to a matrix W, and then a matrix Q, whose columns are the corresponding bases. Because we start with a basis vector, these all are the same size, so all of this is fairly clean. All of these share the same column space. They have to. They span the same vector space. They are constructed to be bases of the same vector space. So the column space of A, the column space of W, the column space of Q are all just different names for the original base vector space that we were dealing with. Because of this, because they represent the same vector column space, the column space isn't changed, they're just linear combinations of each other, they must be related by matrix multiplication, but on the right. Why is this? Well, let's think about what we've already seen in Gaussian elimination. In Gaussian elimination, everything we dealt with was working with rows. And we saw that row operations, some row operation of some A to some B, is equivalent to multiplying A by an elementary operation to give us B. And this relationship between a linear combination of rows and multiplication by an elementary matrix was at the core of all of the LU decomposition, the matrix inverse, and so on. Well, what if we, here we're dealing with columns, right? And so it's not necessarily clear that the same things work out, but what if we were to flip A on its side? What if we were to make the transpose of A, right? Then we could do something working with rows, and this would create some new vector B that we could represent with some by some matrix multiplication. And this I can now turn around. I can take the transpose of both sides, and I would get A, E transpose equals B. Multiplying on the right by elementary matrices is an operation on the columns of A. And just in the same way that we can represent any manipulation of the row space of A by multiplying on the left by a matrix, we can represent by a non-singular matrix, because all of these elementary matrices are non-singular, we can represent column operations, the rearrangements of the column space, by multiplication on the right by a non-singular matrix. This isn't something we're going to be going into too much more, so we'll leave it at this for now. Right? So if A, W, and Q all have the same column space, their columns are all just linear combinations of one another, that means that we can represent this process by matrix multiplication on the right by a non-singular matrix. W equals A times X, some X that represents the orthogonalization process, and Q equals W times Y, where Y represents the normalization process. Right? That, of course, means that Q equals A times X times Y. A and Y are both non-singular, which means their product is non-singular. That means that we can rearrange this by grouping the X and Y, multiplying by both sides by AXY inverse, again on the right, and this gives us that A must be equal to Q times this XY inverse. And we are going to call that matrix, that XY inverse, we're going to call it R. And if we do that, we get this A equals QR. This is the heart of the QR decomposition. I just want to spend a couple more minutes talking about it a little bit more. How can we find this? We can say conceptually it exists, but how do we actually find R? We've seen how we can get Q. It's the process of Gram-Schmidt. But how do we get R? Well, let's think about this. We have A equals QR. And Q is a matrix with orthonormal columns. We've already seen that if you have a matrix with orthonormal columns, then the matrix transpose times itself gives an identity. So let's take this A equals QR and just multiply both sides by Q transpose. When we do that, Q transpose Q becomes the identity, and we're left with R by itself. And on the other side, Q transpose A. This means R is really easy to compute. Once we have found our orthonormal basis, we simply take its transpose, multiply it by A, and we will have our answer for R. Now let's think about what this actually looks like. This means we're taking Q1 transpose, Q2 transpose to Q times Qn, multiplied by V1, V2, Vn, our original set, multiply along a row, down a column. These are giving us dot products. Each entry of R is just a dot product of one of our new basis vectors with one of our original basis vectors. Conceptually, very easy. Right? Because of how we constructed this, because Q was constructed, the set Q, the orthogonal set, was constructed to be orthogonal to all of the earlier ones. So our second vector of our orthogonal basis was orthogonal to the first. The third one was orthogonal to the second and the first. The fourth one orthogonal to the first, second, and third, and so on. This means that a good number, about half of these dot products, are 0. In fact, every time J, the VI, is less than I, we will have 0. This tells us that R has a structure to it. R is an upper triangular matrix. This wasn't something we set out to do, but we find that it results. We have A equals QR, where Q has orthonormal columns, and R is upper triangular. Another decomposition of a matrix into two matrices that each have very special rules. Right? This is upper triangular. Of course, it is not the same upper triangular matrix in LU, but it is an upper triangular matrix. All right. Just to see sort of how we would use this, how can we use QR as a replacement for other problems in the same way we can use LU as a replacement for Gaussian elimination? Well, let's just think about the pseudo-inverse as an example. The pseudo-inverse is really important in finding the solution to potentially inconsistent systems. Remember, if we have a full column rank matrix and AX equals B, we can find an answer, a pseudo-inverse B, and this for any right-hand side. If there is a solution, this will give us the exact solution. If there isn't, it will give us the least squares solution. How can we compute this a pseudo-inverse with the QR distribution decomposition? Well, A equals QR means A transpose A is QR transpose QR. We propagate the transpose through. This gives us R transpose Q transpose Q times R. Again, the Q transpose times Q is the identity matrix, so disappears, leaving us just with R transpose R. Right? That means that a pseudo-inverse, A transpose A all inverse times A transpose, is R transpose R all inverse, multiplied by R transpose Q transpose. But remember, unlike A, which was a often non-square matrix and thus not invertible, R in this context and actually apologies on this. Let me sorry, I've made an error in here because it's a little bit erroneous. I've made an assumption here that is not in fact true. I apologize for that. I will just delete this portion. And I will revisit this again later. I do not believe that we are allowed to do this because R itself is not, in fact, so just to sort of be clear, what I have realized here, R is not square. R actually, oh, never mind. I deeply apologize for this. I am overthinking things here, and this has led to a little bit of a confusion here. Let's erase this pen and go back just to clarify here. What is R? R is built from these invertible matrices, right? These non-singular elementary column operation matrices, if you will. Therefore, R must be square. Q is the same size as A. R is square. Right? And so actually what is on this slide is perfectly correct. Pseudo-inverse from A transpose A, where this is not invertible, becomes R transpose R, where this, each of these A's are not invertible, where each of these R's are invertible. That means that we can propagate this matrix inverse through this product, giving us R inverse, R transpose inverse, times R transpose times Q transpose. And these middle two terms, inverse of R transpose times R transpose gives us the identity and disappears, giving us a simplified form. Once we have the QR decomposition, the pseudo-inverse is a very simple relationship to the original matrix A. If we want to highlight how this compares, compare this to, we had A equals QR, and A pseudo-inverse is R inverse Q transpose. We've flipped the order, take the inverse of one and the transpose of the other. All right. Okay, I apologize for that little confusion on this last slide. But at this point, we have now gone over all of the concepts for Unit 8, ideas of orthogonality, ideas of projections, and the Gram-Schmidt approach for finding a orthonormal basis. In the accompanying worked example videos, we will go through examples of how we use these, how we compute projections, how we compute orthonormal bases, and how we use these to solve applications. Thank you, and goodbye.